Hello, you are welcome to this class. My name is Dr. Kingsley. Okay, in this class, I'll be taking us on first order reaction. In my previous class, I explained what rate of reaction is, factors affecting the rate of reaction, okay, the theories that was put forth to explain the factors affecting the rate of reaction, okay, and I also did a video on rate law, okay, where I talked about what the zero order reaction. In this class today, I'll be talking about first order reaction. First order first order reaction. For the first, I want to remind you, order of reaction simply means ranking of chemical reactions according to how the speed, okay, depends on the concentration. The speed of a reaction depends on the concentration of the reactants, okay, and then we can actually rank different chemical reactions that we have based on what? Based on the way that the speed of the reaction depends on the concentration of the reactant. That is what we call ranking or order of reaction. Order of reaction is a ranking of different chemical reaction in terms of what? How the concentration, okay, affects rate. So there are some reactions in which the concentration of the reactant does not affect the rate of reaction. That is to say that what the rate of that reaction does not depend on what? On the concentration of the reactant at all. Meaning that what? If you use 1 billion, okay, reactant concentration, or you use, okay, 10, okay, reactant concentration, the rate is not what? Is not affected. Now there are other set of what? Reactions in which the rate of the reaction is directly proportional to the concentration of the reactant. That is one of the reactant raised to the first power. That is what we call the first order reaction. In first order reaction, we know that rate is proportional to what? Concentration, okay, raised to some certain power. Okay, this power is x, is called the order of a reaction. Okay, now if this x, which is the order of the reaction, is 1, we will be having rate to be proportional to concentration of the reactant A. Okay, because we are talking about what? A reactant A going to what? Going to products. Okay, so the rate of reaction, if it is proportional to the concentration of the reactant raised to the first power, we say that that reaction is first order reaction. Now you can see that the first order reaction is very important because there are so many chemical reactions that are first order, and there are applications of this of these first order chemical reactions that we will see later. Now if we introduce a constant, our R, which is rate of reaction, will be equals to K1, okay, into A raised to power of the first order. A here is concentration of what? The reactant raised to the first order. Now, what is a K1? K1 here is equals to what? Rate constant. Rate constant, okay, for first order reaction. That is the rate constant. What does it tell us? It tells us that what? That rate is actually equals to K1, because anything raised to power 1 is still the same thing. It's concentration of what? A. That is rate. Now, from mathematics, we know that what? That from this equation, the rate of first order reaction will be directly proportional to the concentration of the reactant, which is to say that if the concentration of the reactant increases, the rate of reaction what? Will increase. If the rate, okay, the concentration of the, okay, the reactant decreases, the rate will also what? Decrease. That is to say that if we plot a graph of what? Rate, okay, rate against what? Against concentration, against concentration of the reactant, it will be a straight line what? Graph starting from the origin. Meaning that the rate for first order reaction increases as what? As concentration increases. Now, having seen this, okay, we'll go to what we'll call the differential rate law for first order. Differential rate law for first order reaction. The differential rate law for first order reaction. Now, A react to produce what? To produce a product. Okay, the rate of the reaction will be equals to minus change in concentration of the reactant, okay, divided by change in what? Time. Remember, the negative here shows that the concentration of the reactant decreases with time. So, and this we have shown to be equals to K1, okay, into what? Concentration of what? Of A. So it's K1 concentration of A. Now, if we look at this, we can see that what? That minus change in concentration of what? The reactant divided by change in time become equals to K1, okay, change K1 concentration of what? Of A. This we have here is what we call the what? The differential rate law for first order reaction. Is telling us that what? The rate of reactant is decreasing with what? With time. And that rate is what? Is proportional to the concentration of a reactant. Now please give me a marker. Now, having seen this, we see that what? That we can get the integral rate law, okay, for first order reaction. What is the integral rate law? The integral rate law is when we integrate the differential. So the differential rate law says that minus change in concentration of A over change in time will become equals to what? K1 concentration of what? Of the reactant. Now we can rearrange before we what? We integrate. Okay, if we cross multiply, you see that our change in concentration of A, okay, become equals to K1 concentration of A, the reactant, multiplied by change in what? Change in time. Okay, let me with the marker. Now, that is to say, if we divide both sides by what? If we divide both sides by A, we'll be having minus change in concentration of A over concentration of A will be equals to K1 multiplied by what? Change in what? Time. All right. So if you look at this, we have finished rearranging, okay, this what? This differential what? Rate law. We can now start what? Integrating. Now I want to integrate. We are having the integral minus integral of change in A, okay, over what? Over A will be equals to K1 integral of what? Of the T. Remember, we are bringing the constant out because we don't integrate what? Constant. Okay? And we are also bringing the what? The negative out. Now, if we integrate change in A over A, what we will have will be ln, okay, of concentration of A over, okay, over concentration of what? Of AU. Okay, our A here now is what? Is a final concentration, while A naught is what? The original concentration. And that will give us, we integrate change in time, it will give us what? It will give us a T. So that will be having minus k what? K1 multiplied by t. Remember what is happening. So this one have what? Have a negative. Now, having gotten to this, we can take this one as what? As our integral rate law for what? For first order reaction. Now, but we can get many other things from here. If we take what? Take exponents of both sides. If we take exponent of both sides, what we'll have is what? Exponent ln a over a naught will be equals to what? Exponent minus k t, k1t, k1t. So when we have that, what will happen? We will see that what? That exponent will cancel ln. Exponent will cancel ln. When the exponent cancels ln, we have what? Concentration of A over what? Over AO. Okay? Will be equals to what? Exponent minus K1 multiplied by T. Now, if we cross multiply here, what we'll now be having is that our A, that is final concentration, will be equals to what? Initial concentration exponent minus what? Minus kt. Remember, this is another, okay, integral rate law, just by rearrangement. Now you see that what? That this t is what? The time of reaction. Yk1 is what? The rate constant for first order reaction. Okay, now having gotten this, we can get what? So many things from here. Okay, if we want to take lane of both sides now, let us take lane of both sides. Okay, take lane of both sides. If we take lane of both sides, what will we have? We'll have lane final concentration will be equals to what? Lane of what? Initial concentration, okay, exponent minus k1t. Okay, so this is a product. So that means that our lane A will be equals to the lane of what? AO. Okay, then minus k1 what? T, because the lane here will cancel what? Exponent, so that this will become minus k1t. Now, having gotten this, you find out that what? That this can also be taken as our what? Our integral rate law for, okay, first order reaction. Now, what does it mean? We can rearrange this as such. Lane A, okay, is equals to minus k1t plus lane initial concentration. So when you look at this can be taken as y is equals to what? Is equals to mx plus what? C. What does it mean? If we plot a graph of what? Of a lane of final concentration against time, our slope will be what? Minus k. And our intercept will be what? Lane of what? The initial concentration. So that is to say that what? If we plot this graph here, we are plotting lane A against what? Time. Okay, we have what? A negative what? Slope. Negative slope. So our slope should be what? Negative. And that slope should be equals to minus K. Then intercept, okay, C, intercept on y-axis, C, should be equals to what? Should be equals to what? Lane of initial concentration. So it's a straight line what? Graph. Okay, that is how you identify first order reaction, that you plot lane of final concentration against time. It will give you a straight line graph in which the slope is what? Negative, and the intercept is what? Is a lane of original or initial concentration. Now, having taken this, you see that earlier we got that what? That lane concentration of what? In final over that of what? Initial is equals to minus KT. Now that means we can remove this negative. If we want to remove this negative, we can take this up and this down. So when we take lane AO over A, it will give us what? KT. Also, okay, know that this can be gotten from what? From this. All right. Now let us take the half-life of a first order reaction. Okay, half-life of first order reaction. Half-life of first order reaction. Okay, we can go with this. So when we are having lane initial concentration over final, to give us what? KT. Now what happens at half-life? We know that what? That at half-life, okay, at half-life, my final concentration will be initial concentration, okay, divided by what? Divided by 2. That is, half-life is the time taken for the original concentration to be halved. So anytime our final concentration is half of what? The initial concentration, our time will become what? T1 over 2. Okay, so when we put here, we have lane of what? Initial over, instead of what? Final concentration, we'll put this, becomes, okay, final over 2, which will be equals to K. Okay, since this is halved, our time will be what? Will be halved. That is half-life, half of the life. So when we see this, you see that what? That AO can cancel what? AO. When AO cancel AO, remember 2 comes up. The 2 comes up. So that we'll be having lane 2, okay, will be equals to what? Will be equals to K T1 over 2. So if we make T half, the half-life, the subject of the formula, what we'll be getting is that T1 over 2 will be equals to lane 2 over what? Over K. Okay, lane 2 is still the same thing as 0. When you take lane 2, you get 0.693 over K. So this is half-life for first order reaction. Now what does it tell us? It tells us that what? The half-life of first order reaction does not depend on the concentration of the reactant, although the rate depends on concentration of the reactant directly. But the half-life is independent of concentration, but depends on what? On the rate constant. The more the rate constant, or the higher the rate constant, the smaller the what? The half-life. Okay, the higher the half-life, the smaller the what? The rate constant. So that is for first order reaction. So in a summary, we can summarize first order reaction this way. Okay, Let us summarize first order reaction. In summary, we have what? First order reaction, differential rate law. Differential rate law. The differential rate law, okay, let us take features here. First order. What is the differential rate law? R is equals to K1, or is equals to minus the A over the T, which is equals to what? K1 concentration of what? A. Then integral rate law, okay, for first order reaction gives us concentration of final concentration, lane of final concentration will give us lane of initial concentration minus K1T. Okay, so we can take what? Graph number 3. Graph. Okay, we see that what? That the graph, if we plot a graph of what? Of lane A versus time. If we plot graph of lane A versus time, it will be what? It will give us linear graph. It will give us linear graph. Okay. Then number 4, we take half-life. If we take the half-life, okay, the half-life T1 over 2 for first order reaction is equals to ln 2 over K, which is same thing as 0.693 over what? Over K. Then we take what? The types of reaction. Examples, types of first order reaction. Number 1, we have hydrolysis of esters. That is acid hydrolysis of esters. We have acid hydrolysis of esters, okay, amines and the carbohydrates. Okay, these are the reactions that are first order reaction. Also, decomposition of dinitrogen 5 oxide and ozone. These decompositions, they are also first order reaction. Also, radioactive decay, radioactive decays are also what? First order reaction. So in my next video, I'll be telling you the applications of these first order reactions. I'll be telling you how they are applied, like in radio dating, okay, carbon radio dating, okay, and so many other things, like what? Like determining the timing of drugs, okay, and dosage of drugs. Then I'll be okay, taking some calculations concerning first order reactions, okay, to determine so many of the parameters. I hope you have enjoyed the class. Do subscribe, share and like, because it will help those preparing for exams such as AP, GCSE, okay, SAT exam, UTME, NECO, WAEC. Thank you very much.